Hi everyone, and today we are looking at an O-level type of question that has to do with properties of circles. And as you can see in the question, we have circles and we have a lot of different lines and angles. So before we actually jump into the question, I would like to do a quick recap on the various types of properties, of angle properties, I should say. And so the first one that we have looks a bit like this, and from the center going out to the circumference, and from these 2 points, same points, we go to the circumference again, and if this is x, this will be 2x. So what it's saying is that the angle at the center is actually the 2 times of the angle at the circumference. And then another one is from the center. If you drew the diameter, that means the line cutting through the center of the circle, and then you just form any triangle with this vertex touching the circumference. This part will be 90 degrees, and we can say that the reason or the property is that there is a right angle in a semicircle. Next, you can say for circle, if let's say you just pick 2 points, and from these 2 points you have an angle x, then from the same 2 points, if they went to a different point on the circle, as long as there's the same 2 points it starts from, it will also be x. This will also be x, simply because they started from the same 2 points and it went to somewhere on the circumference on the circle. And so we call this property angles in the same segment are equal. And then finally, we have, for the final angle property of a circle, we have some cyclic quadrilateral, which simply means that it's a quadrilateral shape with 4 sides, and all 4 corners lie on the circumference, as you can see over here. And then we can say A, let's call this A, and then angle A, angle B, angle C, and angle D. And now you'll see why I color-coded them, because this property says that angle A plus C gives me 180 degrees, and angle B plus D will also give me 180 degrees. And so it means that the angles in opposite segments, they are supplementary. Supplementary means they add up to 180 degrees. And so the reason that you can give, or the property you can give, is that angles in opposite segments are supplementary. And supplementary, think of this sum to 180. That means if you add them together, it gives you 180. And right now, let me just quickly recap what a segment is. If I just draw a circle, basically if I cut the circle from a point on the circumference to another point on the circumference, what I get, this is a segment. And this is also a segment, so I really split it into 2 segments. And that's why you can see in this example over here, the angles in opposite segments, like say A and C, because you could technically split down this circle down this way. Then you would say that this is one segment and this is another segment, and so A and C are angles in opposite segments, right? And I should contrast this with the concept of sector. So this is segment, and I could also have, if I cut it not from circumference to circumference, but I cut it from the center now, out, what I get, now this is a sector. That's the difference. And there's also one more property that I'd just like to touch on. Let me just put it over here. And that is, if I have a circle and I have a tangent. So a tangent is basically a line that touches the curve at one point, right? It touches it only one point over here. And then from this point of touching, I draw a line and I join it to the center of a circle, let's say O. Then this angle over here will be 90 degrees. It will be. And so we call this property, the tangent is perpendicular because it's 90 degrees to the radius. Because this is my radius, right? It's from the center all the way out to the circumference. And there you go, a quick recap, some of the properties of a circle. And based on this, we're going to jump into the question. So over here, in the diagram, AB is a tangent to the circle with center O. So immediately you can see, maybe we can apply that concept. You can see that AB is a tangent to this circle of center O. So immediately, honestly, like you can see this has to be 90 degrees over here based on this property, right? Based on this property. And then it also says that angle CAB is 62 degrees and CDE is a straight line. That means it doesn't bend, right? It goes straight. That means this is 180 degrees. Cool. So part A is stating your reasons clearly. Find angle BDE, and so let's label that. We're trying to find BDE, which is this angle. Okay, and so we can see that it's not, here's how I think about it. It's part of this triangle. This is the first thing I noticed. And I don't know much about this triangle, if anything at all. The only angle I'm given is this. And I deduced from what they told me that this is 90 degrees. But this 90 degrees is not even part of this shape. So maybe let me look at this 62 and see what I can deduce from this 62. I can see that it comes from these two lines. And wait, from here also comes out these two lines. What property does that look like to you? This and this. So maybe let me color code it. We're going for this and this. Angles in the same segment are equal, right? Look here, angles in the same segment are equal. And so, based on that, we know straight away that this angle must be 62 degrees. And then we established just now that CDE is a straight line. That means this is 180 degrees. So BDE must be 180 minus 62. So the first step we can say is that, let's show all our working, is that angle CDB equals to 62 degrees. And then we say angles in same segment are equal. And then we say that angle BDE therefore must be 180 degrees minus 62, which will definitely give me 118 degrees, and this is because angles on a straight line sum to 180 degrees. So there you go, 180. Next step, next part, angle EBO. So let's look, where is angle EBO? Okay, it's now asking me to find this angle. So of course, we already found that this is not a question mark. Let me erase that. This is now 118. And now we're trying to find angle EBO. So let's think about it. What do we know now? Oh, right. Okay. Here's what we can do. This angle 118 is part of this cyclic quadrilateral, right? So the first step is always think, what shape is this angle a part of? So if this is 118, that means this angle must be 180 minus 118. How do I know that? Because it's a cyclic quadrilateral. So I think about the property that I know of a cyclic quadrilateral, which is angles in opposite segments are supplementary, meaning they sum to 180. And so it means 118 plus this angle must give me 180. So I take 180 minus 118. And so that gives me 62 degrees. So this is 62. Yep. So let's just think about it. And the next step is we see that 62 degrees is a part of this triangle. And I see, oh, it's very nice. Like there's a part going here and there's a part going here. It looks like angle at circumference and angle at center. So let's see, angle at center is 2 times the angle at the circumference. So the angle at the center over here is 2 times the angle at the circumference, which tells me that this angle over here must be 62, the angle at the circumference, times 2, which gives me 124 degrees. Yep. And so from there we can solve for isosceles triangle. So actually let me just write down the working. So step 1, we see for angle EBO, let's find angle BFE. So angle BFE is equal to 180 minus 118, 62. And the reason is that angles in the opposite segment are supplementary. And the next step, we see that we can find angle BOE using the property where angle at center is 2 times angle at circumference. So we say BOE is actually 62 degrees times 2, which gives me 124. And we say it's because angle at center equals 2 times angle at circumference. And finally, now we see that this is 124. What is the angle that we want to find? One thing we need to note for sure is that these two sides are the radius of the circle, right? From the center, we go out to the circumference. So these two are the radius or radii. And so that tells me they are the same length. So that tells me that they must be equal. And so really, this is an isosceles triangle. EBO is an isosceles triangle because these two sides are equal. And so to find angle EBO, that's the last step. So angle, write it here, EBO, we take 180 degrees and we subtract away the angle here, which is 124. And then we divide that by 2 because it's an isosceles triangle, so both angles are the same. Because they're isosceles, it means this angle and this angle are the same. So we divide them by 2. And what do we get? We get 28 degrees. There you go. Of course, we put to 1 decimal place 4 angles. And now we're going to go for part B, find angle ABE, and hence write a statement about the lines CA and BE. So let's look at angle ABE first. So angle ABE. Okay, so actually we've already found this angle now. This angle is from the previous part, 28 degrees. So this is 28 degrees. So if this is 28 degrees, and this is 90 degrees, that means ABE, it's not difficult to find anymore, ABE. This must simply be 180, subtract away 90 and 28. So let's do that. 180 angle ABE equals to 180 degrees, subtract away 90 degrees, subtract away 28 degrees, And what we get is 62 degrees, and we can say angles on a straight line sum to 180 degrees. And hence write a statement about CA and BE, lines CA and BE. So let's look CA, BE. Okay, we found that this angle is also 62 degrees. That means this angle is also 62 degrees. So if this is 62 and this is 62, what does that tell me? I think it's clear that over here you see a Z. So maybe let me draw it out. Really what we're looking at is this Z, like this, of which this is 62 degrees and this is also 62 degrees. That tells me that these two must be parallel. That's why they are equal. 62. These two angles are equal by alternate angles. Alternate angles. So what can I say about CA and BE? I can say lines CA and BE are parallel since angles ABE and angle, what's the other angle again? ABE and CAB are equal. There you go.